Hey guys, welcome to this week's lecture. Let's get this guy full screen. That's not it either. There we go. Okay, so let's start this going. We'll keep it nice and easy, hopefully. I think this bottom box here will stay there, but that's all right. So today's lesson is going to be on the basic concept of probability, and then we're going to move on from there to the addition and multiplication rules of probability. Okay, so key concept in this first part about the basics. We were talking about how to interpret these probability values, which are always values between 0 and 1. Okay, so that is a really, really big idea here. That's something that always messes students up. Probabilities are always between 0 and 1. Now, if you convert those to a percent, we talk about those as like chance. So we'd say something like flipping a coin, I've got a 50% chance of getting heads, but the probability of getting heads is 0.5. Okay, so if I ever ask you for a probability, it is never a percent. All right, so a small probability such as 0.001 is something that rarely occurs. We actually say that as something that has a probability of 0 is impossible to occur, and something with a probability of 1 is for sure to occur. So say, like, for instance, the probability that you are in the room with me right this minute as I am recording this is 0 because I am by myself. However, the probability that you are looking at some sort of screen, no, that's just not even, but the probability that you're breathing right now while watching this video is 1, because if you're not watching the video, you're dead, and I'm sorry. But let's move on. So the last little bit, we'll talk about odds. It's really just a ratio of probabilities. It's going to be something really simple. We'll just touch on and move on. So there's a couple definitions we got to have before we can really get talking about anything. The first is an event. An event is a collection of results or outcomes of a procedure. So a procedure is whatever the thing is that we're doing, whatever trial or kind of experiment or activity, whether it's flipping a coin, drawing a card, spinning a spinner, randomly choosing a person out of a crowd and asking them if they have ever gone to college. That is the procedure. So an event is some collection of possible results or outcomes. A simple event is something that cannot be broken down any further. So if we think about a standard six-sided die, so there's a few concepts that we're going to talk about a lot when we're talking about probability in chapter 4 that you guys need to make sure that you are comfortable with, and that is the standard fair six-sided die, standard two-sided coin, and a standard deck of cards. Okay, the first two I can really quickly explain. Six-sided die is just a cube. If you've never seen one before, a cube, numbers 1 through 6 on each side, giving us all the numbers. It's not weighted, which means it's not going to fall to one number more than any other time. Standard coin is any quarter, anything like that. Again, not weighted, so it's not going to fall to one side more often than the other. If you're unfamiliar with the standard deck of playing cards, just Google standard deck of playing cards, look at images, and it'll break it all out into you for suits. If you really aren't sure what it is, email me and I'll send you a picture of that kind of breakdown and I'll talk about it. Those three things are examples we're going to use a lot, and we're going to talk about those and kind of those processes, so make sure you're familiar with those. So back to what we were talking about with simple events. If you talk about our six-sided die, a simple event would be something like getting a 1, but a non-simple event, or just an event, would be something like getting an even number or getting something greater than 4. Okay, those can't be. So getting a 1 can't be broken down into any further smaller or simpler events. And the sample space for a procedure is the listing of all possible simple events. So for a coin, that's simply, if the procedure is flipping a coin one time, then the sample space is simply heads and tails. But if we talk about flipping the coin twice, then our sample space grows to, we can have heads, heads, tails, tails, heads, tails, and tails, heads. So as we start to get more and more kind of repetition of procedures or anything like that, our sample spaces can get very large very quickly. So here's an example of something where we talk about giving birth. So there's a single birth where we assume binary gender identity here, at birth at least. And so we use a little b to denote baby boys, a little g to denote baby girls. So we can see on this table, the left side, we've got the procedure, okay, a single birth, an event, also a simple event, is having one girl, and our sample space is simply boy or girl. But if we expand that out to 3 births, okay, then an event could be 2 boys and 1 girl, okay. It doesn't specify kind of what order that happens in. It's just saying that there are 2 boys and 1 girl. So we could have boy, boy, girl, boy, girl, boy, girl, boy, boy. All of those result with 2 boys and 1 girl. And the sample space there, you can see it right here. I won't read it out for you. So you can see just during this process with 2 outcomes, boy or girl, when you went from 1, you had a sample space of 2 events. When you went to 3 times, your sample space became 8. So it gets very large very quickly. If we did it 4 times, we'd have 16. So simple event, we kind of already talked about this, right? 1 girl is a simple event. You can read through these. With 3 births, 2 girls followed by a boy is a simple event. Now notice the difference between 2 girls followed by a boy. That's not 2 girls and 1 boy as the next thing states. It is specifying girl, girl, boy. And so that creates a simple event, whereas just saying 2 girls and 1 boy is not a simple event. Okay. These 3 different types of notation. So capital P represents probability. So that's kind of how we're going to talk about these things when instead of writing out all the time the probability of blank, we're going to use capital P. And then A, B, and C are typical variables that we use to represent different events that we're talking about. So if we have a problem that say, our 3 births, we could say let event A being having 2 boys, event B is having 2 boys followed by a girl, event C could be having at most 1 boy. So you can kind of choose them to be whatever you want. And then the way we can combine those is kind of similar to function notation, if you remember back to Math 111 or some previous classes. So this right here would be read as the probability of A. And what this is kind of nice about is we can put the variable in there, or if it's something that we don't want to assign a variable, we just want to list it. It's really easy. We can write it in there. But that P parenthesis something, close parentheses, is always just, we're finding the probability of that something happening. Okay, so make sure you guys understand these notations if you need to go back. As I said, probabilities are always between 0 and 1. Okay, so kind of some common ideas, right? You look over this chart here, a 0, probability of 0 is impossible, a probability of 1 is 100% certain. Okay, anything very close to 0 or very close to 1, and that very closeness is kind of, it's not fixed. It can change depending on what you're talking about and what your parameters are needing to be. And so those kind of likely or unlikely things can change. Typically, 0.05 is our pretty common cutoff, and we'll talk about that again a little later. So if something has a probability less than 0.05, it's unlikely. If it has a probability greater than 0.95, it's highly likely. And so that's something that we'll talk about a little later as well. And then if it's 0.5, it's 50-50 chance. Think of our good old flipping a coin. So there are 3 common ways that we calculate the probability of an event. 2 of them are mathematical. 1 of them is subjective. And we'll talk about that here in just a minute. So the first way is relative frequency approximation, or sometimes we'll say kind of an observed frequency, and as you can see here. So this is where you repeat a procedure over and over and over, recording the number of times things happen, and then the probability of A would simply be the number of times that A happened divided by the number of times the procedure was repeated. A really common idea here is like with flipping a coin. If I flipped a coin 10 times and I got 6 heads, then the probability of getting a head, according to that repeated process, would be 6 over 10, or 0.6. And so this is the idea of using relative frequency. Sometimes we aren't able to actually identify the theoretical probabilities, which is what we're going to talk about next. It's too complicated of a system, or it's involving people. And so we use relative frequency, where we just do a bunch of observations and record what happens. Okay. Next one, the classical approach. This is the most common way that we do things. And this is where we simply take the number of ways event A can occur and divide it by the total number of different possible outcomes. Now, this requires something very specific, and this requires us to have equally likely outcomes. What that means is the chance for every outcome to happen is the exact same. Okay? So I want to think about something real quick with you guys. I want you guys to draw this out or write this out, if you will. Okay? Imagine that we have a bag with 5 colored marbles in it. In that bag, there's 1 red marble, 1 blue marble, and 3 white marbles. Okay? Now, if I reach in that bag and pull a marble out, my possible outcomes are I get a red marble, I get a blue marble, or I get a white marble. Okay? Those are not equally likely because there's more white marbles than there are red or blue. And so we can't simply say that the probability of getting any one color is 1/3 because that's not the way it works. The way we can do that, though, is if we treat each marble individually, we could say that the probability of getting a red marble is 1/5 because there's 1 red marble in all 5. Same for blue. But for white, since there's 3 white marbles, we could think of each of those 3 white marbles as a distinct simple outcome, okay, or a simple event. If you wanted to think of it as saying like you've got white marble 1, white 2, white 3, and so when you draw them, you can identify which one it is, right? But ultimately it's white, and that's all that matters. And so for the probability of getting a white marble in that situation would simply be 3, the number of ways we can get a white marble, over 5, the number of total possible simple events. So big key in this is equally likely outcomes. Make sure that's something we always have to make sure we have before we do this. A lot of the times we can adapt the way we count things or think about things so that we do have equally likely outcomes. And a lot of the times that's kind of how we naturally will think about how to do these problems. But I just want to make sure that's very clear in our heads. We have to have equally likely outcomes. And the last way is a subjective probability. Okay. Subjective probabilities are simply estimating using knowledge of relevant circumstances. So you could tell me that with almost 100% certainty, right, with almost a probability of 1, I will put out another video by the end of the term. Because if I don't, you guys can't learn anything, right? And you know I'm going to. So the probability that I put out another video in this class before the end of the term is 1, right? We don't have any math to back that up. That is something that is estimated using knowledge of the relevant circumstances, okay? Rounding probabilities, unless specifically said, key takeaway here, 3 significant figures, okay? 3 significant digits. So if the probability of something happening is 1/3, we would just simply say 0.333. Law of large numbers. So this applies back to the first way of calculating probabilities, our relative frequency approach. Okay. In this idea here, we kind of do something over and over and over again. Well, if we think about just our simple coin flip, right? If I only flip the coin 1 time and I get heads, well, according to that, then the probability of getting heads is 1, and the probability of getting tails is 0. In other words, every time I flip that coin, I'm getting heads, and I will never get tails. But we know that's not true. And the reason why is because it's too small of a size. And so we use this idea of law of large numbers. And what this simply says is that as a procedure is repeated over and over and over again, the relative frequency probability, that first one, approaches its true probability, or we say the theoretical probability. And that's our second count, our second type of probability, classical approach. Okay. So as the number of times we repeat the process, as that gets more and more and more, our relative frequency probability will be closer to the true theoretical probability. And this is something that we use in statistics in the idea of getting a large enough sample size that we can accurately project things about the population. Once we get a large enough sample size, once you use enough, you have enough that it is pretty close to the actual probability. Okay. Now, this doesn't mean that if the number is like there's 500 ways for something to happen or there's 5 trillion ways for something to happen. That's not what it means by large numbers. It's about the number of times the procedure is repeated. That's, yeah, you can read that. All right. we're going to do an example involving relative frequency, and we're going to deal with skydiving, right? Skydiving is one of those things that many of us are like, yeah, that's on my bucket list, and some of us are, no way, we're never doing that. So the probability of dying when making a skydiving jump, okay? In a recent year, there were approximately 3 million skydiving jumps, with 21 of them resulting in deaths. So using the relative frequency approach, that's that first one that we talked about, the probability of dying while skydiving in a single jump can be found simply by taking the number of skydiving deaths divided by the number of skydiving jumps, which is just 21 over 3 million, or it rounds to 0.000007. Okay. Texting and driving. Here's another example. Okay. The difference here is that we aren't given a total number. We're told that 3,785 high school students said they texted while driving in the last 30 days, and 4,720 did not. So if I want to find the probability that a randomly selected high school driver, had texted in the last 30 days, I have to first add these two values together to get the total number of drivers in the sample, okay? Or the total number of times this procedure of asking a high school student driver if they had texted in the last 30 days. I have to figure that number out. Once I have that, it's exactly the same as the skydiving problem. Take the number of drivers who texted while driving divided by the total number of drivers asked. We get our probability that someone texted while driving in the last 30 days, 0.445. Okay. Here's another term for you, another definition is complement. The complement of an event. Okay. We denote this by this little bar above our event. So we say a complement is the way we would read that. And that is simply everything that is not A. So if we think about rolling a dice, okay, if I say event A is getting a 1 or a 2, that means the complement of that is getting anything other than a 1 or a 2. So we're getting a 3, 4, 5, or 6. Okay. And so the event and its complement, there is no overlap. They completely separate themselves. And what's really cool about them is they actually take up the entirety of the sample space, because event A is some group of that sample space, and then everything that's not in event A, everything else in that sample space is not in A, is in fact a complement by definition. So coming back to this, there's a 0.445 probability that a high school driver randomly selected has texted in the last 30 days. The probability that a high school driver has not texted in the last 30 days would simply be everyone else over that same number. I think we do that in just a minute. So this is not dying. So they knew this many jumps, that many deaths, found the difference was this, simply 3 million minus 21. Look at that. Okay. So we're not doing the driving one. It's okay. The rare event rule. Okay. I'll let you read through this. This is something we're going to talk about later in this term. It's something called hypothesis testing. This is the idea that we're testing a given assumption, and if things didn't happen by random chance, that assumption is probably wrong, and that's what this is talking about. Okay. So here is kind of what we're talking about with our significantly higher or lower, our kind of extremely likely or extremely unlikely events. And so this is where we get that 0.05. Now, this is not a rigid value. It's not something that is always what we're going to use. That's something that will change depending on the situation that we're dealing with. So I want you guys to read through this. Okay. At this point in time, we're not going to be doing a whole lot of X or more outside of some very simple things. But coming up very soon, we will be coming up with the material next week. And so you want to be able to kind of understand what this is talking about and stuff like that. So if we want to know if something is unlikely, we want to figure out if that value or more, okay, if that probability is less than or equal to 0.05, or similarly, if that value or less is less than or equal to 0.05, we say that that is significantly low or significantly high, okay? Some real breakdowns here. Probability of an event is some sort of number between 0 and 1. It can be 0 and it can be 1, so we can include those. An impossible event has a probability of 0. A certain event has a probability of 1. Okay. We use this notation, P of A, to represent the probability of event A, and P of A complement is the probability of that event A does not occur, or the probability of the complement of A. Okay, so odds. When we talk about the odds of things, we say the actual odds of an event against an event. So this is the odds that something does not happen, okay, is simply the probability of the complement divided by the probability of the event. Okay, now these two fractions both have the same, so these two probabilities would both be found using the same denominator of either the number of times the procedure was repeated, if it was relative frequency, or the number of total possible simple events, if it was the classical approach. And either way, when we divide one by the other, it will cancel each other out. Okay, and that's something that hopefully shouldn't be totally brand new ideas with fractions. If you want to see an example of how that would work, take something like, say, 9/13 divided by 7/13. When you do that, if you use your calculator, if you do it by hand, the 13s are actually going to cancel, and you're going to end up with 9/7. Okay? And so we would say then, if that was the case, we would say that the probability or the odds against this happening would be 9/7 or something along those lines. Okay. The odds in favor of an event is simply the probability the event does happen divided by its complement. Okay. I'm not a big fan of odds. It's not something that I really like to do. It's something I like to talk about so you kind of understand where it's coming from. And what's really nice is to recognize from this that there is no involvement of the total possible outcomes here. There's simply an involvement of kind of the total number of ways. If we add together these two values here, this B and this A, we will get the total number of ways unless that ratio was simplified. Okay. And so odds are kind of something that it's kind of unique and it's used in certain situations. We need to understand what it is, but I don't really worry about it a whole lot in this class. Okay. Now, let's get into the meat of this lesson, the addition and multiplication rules of probability. Okay, so far we've basically said, like, okay, if you know how many ways this thing happened by basically repeating the process, you can find its probability by taking that number of ways it did happen divided by the total number of times you repeated the process. Or if we know the number of ways it can happen, we can divide that by the number of ways all simple events could happen. Okay, and so now we're going to talk about some ways we can get some more complicated kind of probabilities going on here. Okay. The addition rule is a way that we can use to find the probability of event A or event B happening. And it's really important that we focus on that word or. Okay. When we're finding the probability of A or B, that should raise a red flag in your head. Or means addition. Okay. And so we want to use that for the addition rule. Right? If we want to find the probability that two events happen, and it's not just that like A and B happen at the same time, okay? And this is something we're going to break into a little bit more. But if we're finding the probability of A and B, that and should trigger your thought process to think the multiplication rule. Now, with that said, we're going to talk later as well about the difference of probability of A and B in a single trial versus the probability of A and B in a sequential trial process. We're going to talk about that when we get to the multiplication rule. Okay. So, a compound event is any event involving two or more simple events. So, when we talked about an event in the very beginning, we didn't specify that event couldn't be a simple event. So, in general, you either are a simple event or you're a compound event. But either way, you are an event. Okay? Or the thing is an event. So a compound event is something that is at least two simple events. Now, if we're looking at the addition rule, what we're looking at when we say the probability of A or B, we're looking at the probability that in a single trial, event A occurs or event B occurs, or they both occur. So that is what we're looking for. Now, if we think back to that bag of marbles, okay, you remember I had 1 red, 1 blue, and 3 white, okay? If I said, what's the probability that I get a red or a blue marble, okay, what I'm asking is, if I pull a marble out, I have gotten the thing that I wanted if I have a red marble. I've gotten the thing that I've wanted if I have a blue marble. And I've gotten the thing I wanted if I have both marbles, which is impossible because we're only pulling out one. And we'll talk about that in a minute. Okay. And so we want to kind of keep that in mind. We need to be careful when we're doing this that we don't double count. And that's something that can happen very easily. All right. So the formal addition rule, the actual way this formula looks, is we say that the probability of A or B is simply equal to the probability of A plus the probability of B minus the probability of A and B. Now, I know you're sitting here looking at this going, oh, that means multiply. But in this case, it doesn't, okay? Because in this case, we're talking about probability of A and B in the probability that they occur at the same time in a single trial, okay? And that is where we differentiate between the multiplication rule. Multiplication rule is in a sequential trial basis, and we'll talk about that when we get there. Okay, so the probability of A and B here references just in a single trial. All right, and we're going to talk more about that. Let's see here. Here we go. I'll look at this picture. So when we're looking at this picture, ignore the words. I'm going to go back and talk about disjoint and non-disjoint. The reason why we have to subtract the probability of both A and B is because if we look at this kind of Venn diagram here, if everything inside this circle here is event A, and everything inside this circle here is event B, if I simply add everything in A and I add everything in B, I've now added everything in here twice. And because of that, I have to subtract off everything that is in both A and B. Okay, so that's what we're doing here. That's why we do this. If you want to think about it very simply, okay, here's what I want you to do right now. I want you to write out the event space for rolling a 6-sided die. Okay, so pause the video, write that down. Perfect. So what we have in our event space is we could get a 1, we could roll a 2, we could roll a 3, we could roll a 4, we could roll a 5, and we could roll a 6. So those are all of our possible outcomes for rolling a die. So if we let event A be rolling an even number, okay? If event A is rolling an even number and event B, let's say, is rolling less than 3, okay? Not less than or equal to, but less than 3. So what I want to do is in our listing of our simple events, we listed 1, 2, 3, 4, 5, 6, right? I want to kind of underline anytime we have something that satisfies either event A or B. We're going to do one event at a time. So for event A, rolling an even. So what I want to do is I want to go through that list and I'm going to underline 2, 4, and 6. So those were, if I get one of those results, that is satisfying event A. That means event A has happened. Now I want to go through for event B and I want to underline anything that is less than 3. So I want to underline the 1 and I need to underline the 2 again. Now, what's really nice in a fair 6-sided die, every outcome, every simple event is equally likely. So we can really easily apply this classical approach. So in other words, the probability of A or B happening, we can simply add up the number of ways they can happen and divide it by the total number of simple events. So first of all, there's 6 simple events, right? We could get a 1, a 2, a 3, 4, 5, or 6. So 6 simple events. So we're dividing whatever number we get by 6. So if we look at our list and look at everything that's underlined and we count it. So if I get a 1, that means either A or B is satisfied. If I get a 2, either A or B is satisfied. If I get a 4, A or B is satisfied. And if I get a 6, A or B is satisfied. So that right there gives me 4 ways that A or B can happen. And if I divide that by the total of simple events 6, I get 4 over 6. So 4 over 6, if we want to simplify that, we can simplify that to 2/3. Now, if we just added together, like this right here, this mutually exclusive idea, if we just added the probabilities of A and the probability of B, which is what we might intuitively think to do with this, okay, if I do that, so the probability that we get an even is 3 out of 6, okay, because an even number is 2, 4, or 6. And the probability of rolling less than 3 is 2 out of 6, which is because we can have a 1 or a 2. If I add those together, that gives me 5/6. But the problem is I double counted that 2, right? I included rolling a 2 as both satisfying A and satisfying B. But if I get a 2, I don't get it. It doesn't count twice. So I have to subtract off that intersection. So that's what we're doing here, okay? Now, if me talking through this example has confused you or you weren't able to follow through with it, back it up a little bit, try listening to it again. And if you're still lost or anything like that, email me and I'll send you a little write-up, or I'll try and just kind of walk you through whatever you're confused on, okay? So now I want to go back to this idea of a disjoint event, okay? This idea of identifying an event being disjoint or mutually exclusive, these two words mean the same thing, disjoint and mutually exclusive, okay? It's very important we're talking about this addition rule. What that means, if two events are disjoint or mutually exclusive, that means they cannot occur at the same time. There's no overlap in those kind of Venn diagrams. There's no overlap in these events. You cannot satisfy both A and B in a single trial. Okay. So if we look here at this example, we have randomly selecting someone for a clinical trial who is male as event A, and event B is randomly selecting someone for a clinical trial who is female. Okay. These two events are disjoint because there isn't, so people cannot be both male and female. Now, we're going to move beyond any sort of social discourse about this. We're just standing with standard scientific binary gender identity here. And not disjoint, if we read this one here, randomly selecting someone that's taking a statistics course, randomly selecting someone who is female. I can guarantee you there are females taking this course, even though you do not see them because you are at home, unless you are a female, in which case you can see yourself and you can see one. So there are females that are taking this course, so there is an overlap of that. So these are not disjoint events or mutually exclusive events. Okay. Now what's really great is if two events are mutually exclusive, okay, so there isn't this overlap, I never double count, so I don't have to subtract this, right? Because if there is no overlap, so A and B cannot happen at the same time, which means that it's impossible to get both A and B, which means that probability is 0. So when I subtract, I would be subtracting 0. So we can simplify the addition rule to just a probability of A plus the probability of B if our events are mutually exclusive or disjoint, same word, same meaning. Okay. If they are not disjoint or not mutually exclusive, we have to subtract off their intersection. Okay. So what I want to talk about here is we're going to talk about the probability that if we draw one card from a standard deck of cards, that the card will be a black card or a 7 card. So again, if you're not familiar with the standard deck of cards, pause this video now, go look at a standard deck of cards. 52 cards in the deck, 4 suits, 2 colors, numbers 2 through 10, plus 3 face cards and an ace card. Okay. So we want to know the probability that if I draw one card from a standard deck of cards, the card will be a black card or a 7 card. So if we let event A be drawn a black card and event B be drawn a 7 card, we can really easily find these probabilities out. So the probability of event A, okay, since we're talking about it being a black card, half of the deck is black. So there are 26 black cards out of 52, and that reduces down to 1/2. If we want to talk about getting a 7 card, there are 4 7 cards in the deck of 52 cards, and that reduces down to 1/13. Now, what's the probability that you get a black 7 card. Well, since there are 2 black 7 cards in the whole deck of 52, that probability reduces to 1/26. Okay. Now, if we look at this kind of image here, okay, we can see we have black cards over here, 7 cards over here, and in here is our 2 black 7 cards. So because if I just add the black cards, probability of getting a black card, and the probability of getting a 7 card, okay, let that go away. We would double count those 2 black 7s. We would count them once when we add the probabilities of getting black. We'd add them again when we add the probability of getting a 7. So we have to subtract off that 1/26 for that double counting, giving us a total of 7/13. Now, I reduced that down. I use my calculator. If you're like, how do I take 1/2 plus 1/13 minus 1/26 and get 7/13? Use your calculator. That's perfectly fine. Okay. If you go back up to here and you don't reduce, so we have our 26 50 seconds plus 4 50 seconds minus 2 50 seconds, okay, you will get 28/52, which represents the 28 total cards that exist within events A and B. Okay. Hopefully this made some sense. Hopefully you guys are kind of understand how to use this addition rule. Okay. If we see or, we need to think addition. Okay. Now, it's very important whether to do this, whether or not they are disjoint or not disjoint, or mutually exclusive or not mutually exclusive. Identifying that is really important because it makes our process really simple, or still fairly simple, just another extra step. Okay. Now, if we think back to our complements, when I talked about that, we said that the totality of event A and event A complement make up the entire sample space. So what's really cool about that is because of that, the probability of A or A complement is 1. Very simply because either you're in A or you're not in A. And so that's everything. So it has a probability of 1. And because they're disjoint, there is nothing that can be in A but also not be in A. So because they're disjoint, our addition rule is very simple. We add the probability of A plus the probability of A complement. Okay. And that's equal to 1. This piece right here. All right, that's cool. This piece right here, this probability of A plus probability of A complement equals 1. This builds us 3 really nice equations. Okay. And what it gives us is this probability of A plus probability of A complement equals 1. Or if I simply subtract the probability of A, right? A complement. Think of these are numbers, right? So we have, say, like 5 plus 7 equals 1. So we can use our same algebra rules to subtract from both sides, cancel on the left, it's there on the right. So we get that the probability of A complement is 1 minus the probability of A, and the probability of A is 1 minus the probability of A complement. These ideas here are really useful in finding some very simple probabilities. Sometimes a question will be asked in a way that's really hard to find the probability of that event happening. There's so many ways it can happen, so many different things you have to calculate. But it's really easy to calculate the number of ways that something can't happen. And so if we can do that, we can use these rules of complementary events to help us evaluate the probabilities we're looking for by actually finding the probability of the complement. So here's an example that uses this. So there was a study conducted that found that the probability that someone has sleepwalked was 0.292. So if we want to find the probability that somebody has not sleepwalked, we can use these complementary event rules. Okay. And we simply can use the fact that the probability that someone has not sleepwalked is equal to 1 minus the probability that they have sleepwalked, which in this case, according to the study, is 1 minus 0.292 or 0.708. So the probability that randomly selecting somebody who has not sleepwalked is 0.708. Okay. So these are really nice and easy rules to use. Multiplication rule. So here's where I talk about this differentiating and. So when we talk about the probability of A and B, representing the probability that event A occurs in a first trial and event B occurs in a second trial, this is telling us that we are going to be using the multiplication rule. Now, this is different than in the addition rule when we had probability of A and B being that intersecting piece where both events happen at the same time. Okay, so imagine, if you will, our bag of marbles. We had the one red, one white, three, or one red, one blue, three white. If I'd say pull a red and then I pull a blue, okay, so I pull one marble out and then I pull a second marble out. There's two events. One's getting red, one's getting a blue. Okay. This next notation here, this is what we call conditional probability. And we're going to focus on this a little bit more next class, I think. We might not. Conditional probability is really simple. It's something that you're just going to take a second and think it through kind of in the number of ways it can happen. And we'll talk about that more when we talk about counting next week. And what this stands for is we read this as the probability of event B given event A has occurred. Okay. So what this is assuming is A has already happened. Now, what's the probability that B happens? Okay. And we're going to see in an example here in just a minute how that affects the probabilities and what goes on. Okay. So intuitively, it's really simple. We simply multiply the probability that event A occurs in trial 1 and event B occurs in trial 2. Now, when we're doing this, we have to use this conditional probability. We can't just say probability of A times probability of B, because the second thing here, we are assuming that A has already happened. Okay. Now, just like with the addition rule, we had that idea of disjointedness, that if two events are disjoint, we can just simply take A plus probability of A plus probability of B. Similarly, with multiplication rule, if two events are independent, then I can just take the probability of A times the probability of B. Okay, but independence here is a little harder to think through. Sometimes it's a little harder to prove. In some cases, the problems will be worded. Sorry about that. They'll be worded to tell us what it is, and in some cases it won't, and you'll have to kind of do some exploration. So we say that two events are independent if one of them happening does not affect the probability of the other happening. In other words, A and B are the same if the probability of B is equal to the probability of B given A. Okay, so if the probability of an event happening is the same as the probability of that event happening when another event has happened, then those two events are independent. Okay, so if we look here, we've got a red and a white dice are rolled. Okay, if event A is rolling a 5 on the red die, and event B is rolling an even on the white die. Okay, then we have another situation where we're considering drawing two cards from a deck of cards with replacement. And we're going to also consider drawing two cards from a deck of cards without replacement. So for each of those bullet points, I want you to think real quick, are these two events independent or not? Okay. Identify if these are independent. I'll wait for you. Pause it. All right. Welcome back. So if we look at this first one here, we have a red and a white die rolled. Event A is getting a 5 on the red die, and event B is rolling an even on the white. Now, if I roll a 5 on the red die, does that affect the probabilities of rolling a even number on the white die? Absolutely not. They're two totally separate die, right? And if you want to be like, well, maybe the white die hits the red die, where you can assume distance or whatever you want to assume, or even if not, it's still random chance if it would have hit a corner or would have hit the die or whatever. Okay, the number on that red die didn't affect it. It was the physical space taking of the red die. The next one, consider drawing two cards from a deck of cards with replacement. And the last one, consider drawing two cards from a deck of cards without replacement. So the difference here is with or without replacement. And so what that simply means is with replacement would look like if I had a deck of cards, I randomly pull one card out, I look at what it is, I write it down, or I commit it to memory, and then I put that back into the deck of cards. And then I randomly draw another card. Okay. If that's the case, so if we have with replacement, then those two events are independent. Okay. Because we are putting the card back, or putting whatever it is back, so we are restoring the original state of things, it is independent. It creates an independent situation. However, if we do it without replacement, it is not independent. Okay. So if I take a card out of the deck of cards and I set it down on the table, and then I take a second card, well, now there's only 51 cards in that stack because I took one out. So every probability is no longer something over 52. They're now something over 51. So all of our probabilities have changed. And because of that, these are not independent. Okay. So let's talk about an example of this. All right. If we have 50 test results from subjects who use drugs are shown below. Okay. So if you will, this is a good old-fashioned drug test, seeing if you've done drugs. There were 50 people that had all done drugs. So all 50 of these people did drugs. 45 of them tested positive, while 5 of them tested negative. Okay. So we have two problems. One, if 2 of these subjects, 50 subjects, are randomly selected with replacement, okay, find the probability the first selected person had a positive test and the second selected person had a negative test. So notice here that we have with replacement. So these are independent events. In part B, we're doing the same exact thing, but now without replacement. So these are dependent events. Okay. With that replacement, the first selection having a positive test result is 45 over 50. The second selection having a negative result is 5 over 50. Those are exactly the probability of getting a positive and getting a negative any way possible. Okay. So we multiply those events, those two things together, and we get a probability that we have the first person is a positive result. That person goes back. We draw another person, and that person has a negative result. Is 0.09. Now, if we don't replace, the first probability stays the same. The first probability of somebody getting a positive test is the same. The difference is the second probability of getting a negative test, because there's still 5 of those people, but now there's only 49 people to select from. So the second probability, the probability that the person has a negative test, is 5 over 49 instead of 5 over 50. And so when we multiply those together, we get a probability of 0.0918. So when we replaced the person back in, the probability that we got this positive test to the negative test was only 0.09. But when we didn't replace that person, the probability went up a little bit to 0.0918. So that's a very important idea to understand. And notice the difference in calculation was simply that we had to refigure this value, assuming that the first thing had happened. This just reiterates what I've already said, that with replacement is independent, without replacement is dependent. Now here's a nice fun problem here that is maybe terrifying to some people who are already terrified of flying, but it's okay. This hopefully will calm some of those fears. Airlines build in redundancies so that if something fails, there's other systems there that do the same job, and so that the plane doesn't go crashing down if one little thing fails. So in an Airbus 310, if it were to only have one hydraulic system, what's the probability the aircraft's flight control would work for a full flight? So the hydraulic system is what helps control the flight, control the controls. Okay. And what we're told here is that the probability that a hydraulic system fails is 0.002. Part B says the Airbus 310 actually has 3 redundant, independent hydraulic systems. In other words, each hydraulic system operates independently of the other. If one breaks, it doesn't affect the other 2. So if we have 3 of them, what's the probability that control can be maintained throughout the entire flight? Well, if we know the probability that it fails, okay, we can use that very simply. If we have a single hydraulic system, the probability that it fails is 0.002. That means the probability that it doesn't fail, using those complementary rules, is simply 1 minus 0.002, or 0.998. So if we only had one hydraulic system on this plane, the chance that it would maintain control throughout the entire flight is 0.998. It's pretty high probability. But now what if we have 3 independent hydraulic systems, which these things actually do? The probability that all 3 of them fail. So for this plane to lose control, all 3 systems would have to fail. For all 3 systems to fail means that the first system failed, the independent second system failed, and the independent third system failed. So the probability of that happening is 0.002 times 0.002 times 0.002, which gives us this 0.000000008 probability. Okay, which means the probability that we do not. So this is the probability that all 3 fail. So that means the probability the plane maintains control is 0.999999992. So for those of you who are worried about flying, there's very, very, very high probability that they will maintain control throughout the entire flight. You can read through that. I'm not going to waste my time. So here's kind of a summary of these addition and subtract rules. When you see the word or, think addition. Okay. First thing you should do is identify, are these 2 events mutually exclusive? Are they disjoint? And then use the appropriate addition rule from there. If you see the word and for 2 trials, you need to think multiplication, and you want to identify, are these events independent or are these events dependent, and go from there. All right, you guys, that's it. That's the end of this lesson. Get after this assignment. Some of these problems, I'm not going to tweak the assignment. I've created the assignment in the past where I just have one big assignment for chapter 4, and I'm going to leave it at that. I may add some problems. I may take some away. So if you look at a problem and go like, I don't know how to do this, don't. Wait until next week after we get that material, and then you'll be able to do all of these problems, okay? All right, you guys, that's it. Have fun. Let's see if I can figure out how to stop this video. Don't want to embed webcam.